And now we're going to look at characteristics 2 and 3. Horizontal and oblique asymptotes. And this is where the three groups come in. Okay? And I feel like the textbooks, they over-explain it a little bit here, but if you have the bigger function in your denominator, this one has an x, it's a line in the bottom, has a bigger degree in the bottom, you will always have a horizontal asymptote at y equals 0. So you can have a line over a parabola or a constant over a line. As long as the degree is bigger in your denominator, you have a horizontal asymptote. Maybe I can do that. Horizontal asymptote at y equals 0. Okay? If you like thinking of this compared to what we did in section 2.2, that was group 3. Group 3 always had a degree bigger in your denominator. Every single time you're going to get a horizontal asymptote at y equals 0. Next, this was group 2. Same degree in your denominator and your numerator. That also gives you a horizontal asymptote, but now you would look at the coefficients. So I'm going to take out a little tiny highlighter here. There's a 2 in front of the x there. There is technically a 1 in front of the x there. 2 over 1 would tell you that you would have a horizontal asymptote at y equals 2. The textbook gives a much more complicated way of describing that. You don't need to know the complicated way. It's as simple as that. If it's the same degree on the top and the bottom, horizontal asymptote at the coefficients, you're going to have it at y equals 2. Kind of a cool explanation, and it kind of connects to the last one, which is group 1. With no holes. If you have a parabola over a line and nothing simplifies to give you a hole, you will always end up with an oblique asymptote. And to find the equation of the asymptote, we get to go back to our polynomials unit and actually use synthetic division. So if I divided x squared by x plus 1 in synthetic division, and that's right here, here's the setup. Remember, you have to put in zeros when things are missing. And you do your synthetic division, and whatever your answer is, ignoring the remainder completely, even if the remainder is like 17 billion, like the craziest, biggest remainder, you're like, wow, that's a huge remainder, you can ignore it. Your oblique asymptote will just be what's left if you ignore the remainder. And the reason for this is the following. Okay? If we took y or x squared over x plus 1, right? You had a division statement. Remember this? So technically, the division statement for x squared divided by x plus 1 looks like this. X squared equals x plus 1. We got a quotient of x minus 1 and a remainder of plus 1. That's your division statement from chapter 1. If you divided everything by x minus 1, oops, plus 1. Wow. Okay, let's try that again. If you divided everything by the x plus 1, you'd be left with an x minus 1, and the 1 would have to also still get divided by an x plus 1. And horizontal asymptotes or oblique asymptotes, again, they happen when x is going to extremes. So our question is, what happens to this as x gets really, really big? This part right here gets really, really close to 0. And it wouldn't matter what remainder is on the top, with an x on the bottom, it would always go to 0, leaving you with just the equation that's left as your oblique asymptote. Now, they won't ask you to describe why oblique asymptotes work. All you'll need to be able to do is say, recognize if I have a parabola over a line, I have group 1 with no holes, then I'm going to get an oblique asymptote. And then I can use synthetic division, and whatever I get as the answer becomes my oblique asymptote. Okay, so with that, we're ready to go to this example. I can take our instructions and move them off to the side again. Just big enough so we can read them, or pretend to read them. So, step 1, we factor completely. This factors nicely to be x plus 7, x minus 1 over x plus 2. Once we've factored, we write out our non-permissible values. Only what you're dividing by, because you're not allowed to divide by 0. So x can't equal negative 2. Does it cancel out? No. Since the non-permissible value doesn't cancel out, that tells us we'll have a vertical asymptote at x equals 2. So notice when we say the non-permissible value, we put the line through to say it can't equal that value. But when we write the equation of the asymptote, it's an equation. It has an equal sign. Okay. So, which group do we have? We have group 1. Degree is bigger on the top, and there's no holes. So this means we are going to get an oblique asymptote in this situation. How do we find our oblique asymptote? We use synthetic division, 1, 6, and minus 7, divided by x plus 2, so you have a minus 2 out in front. Bring down the 1, negative 2, 4, negative 8. So we ignore the remainder, and y equals x plus 4 is our oblique asymptote. So did step 1, factored completely. Step 2, did our non-permissible values, figured out that they were vertical asymptotes. Step 3, we recognized that this was degrees bigger in the top than the bottom. It didn't simplify, so then we're going to get an oblique asymptote. Okay? At this stage, I like to start my graph. So I know that I have a vertical asymptote at 2. And I can label it x equals 2. My oblique asymptote is a line. A line with a y-intercept of 4 and a slope of 1. So I could go over 1, up 1, over 1, down 1. It's going to get in the way later. Okay. Now, it is only the vertical asymptotes that separate your graph into different sections. So technically, this graph has 2 sections. Left of x equals 2 and right of x equals 2. In order to finish this graph, we need to label all of our x-intercepts, our y-intercept, and then see if we need any other nice points. So, y-intercept is always the easiest. In fact, I'd go back to my original equation, because if you plug in 0 for x, it's really easy in the original equation. Can you see that you would get negative 7 over 2, which is negative 3.5. So I'm going to go to my graph. 1, 2, 3, 4. And I'm going to label 0, negative 3.5. X-intercepts. Okay? X-intercepts are only going to happen when your numerator is 0. So you can ignore the bottom. And if it's already factored like it is, can you see that your x-intercepts are negative 7, 0, and 1, 0? Is that right? Did I do it in the wrong direction? Negative 7 and plus 1. Uh-oh. Did someone see a mistake I did? Nobody told me? You guys are supposed to be nice to me on a Monday. Anybody see the mistake I made? It's like typical, you probably don't recognize it because it's like, that's a mistake I make all the time. What did I do? I asked him to which one? The vertical one. Do you see how I wrote x can equal negative 2? And then what did I do in the next step? I forgot the negative. Oh. Do you guys do that all the time? Sometimes. Okay. Oh my goodness. So if you were, maybe to make your notes nice, you just ignore this one, right? Because this one's wrong. I don't know if you want to erase it. This is where it should be. Oh my goodness. I'm going to erase mine. There we go. Okay, I'm sorry. So we have an x-intercept at 1, 0, and 1, 2, 3, 4, 5, 6, 7. Negative 7, 0. Your vertical asymptote breaks your graph into 2 sections. We have to decide, do we need more points or are we good? Do you have any points left of x equals negative 2? We do. Technically, this is enough for us to go toward this asymptote in this direction and this asymptote in that direction. It feels a little bit weird. That is all you have to do in that section. Go towards the asymptote. Don't make any new x-intercepts. Can you see that that's why it has to go down in this direction and up in that direction? These two, well, you can join them, and then it has to go towards the asymptote there and towards the asymptote there. One of the E errors is the E10 error. That's an asymptote error. So I'm going to show you some examples of E10 errors. The blue graph right now is fine. But if you did this, oops, and went through your vertical asymptote, you're going to get an E10 error. So that would be a problem. You also can get an E10 error. This one's a little bit interesting. Is you get close to your asymptote, and then the last second you decide to go away from it a little bit. The asymptote is there that your graph keeps getting closer and closer and closer to it. If you get close to it, then decide, I'm just yawn right at the end of your question and Don't take your time and have it swing away. That's going to be another E10 error. Okay, so this is our first graph with an asymptote. It's kind of, sometimes with these asymptotes you'll get the graph in these two little sections, and sometimes it's on the outside like this one. All right, let's do part B. There's room on the next page at the top to do part B if you've used it all up, or you can do it on the page 108. Oh my goodness. There we go. It's the exact same numbers, so factoring is easy for us. So step 1, factor. Step 2, look for non-permissible values. X can't equal -7, and X can't equal 1. And we have to decide, are these going to be wholes or vertical asymptotes? Well, they don't simplify and go away, so we're going to have 2 vertical asymptotes. One at X equals -7. Notice how I strategically did not forget the negative this time. And the other one at X equals 1. We have a line over a parabola. The degree is bigger in the denominator. This is group 3. Group 3 is the easiest one. Whenever the degree is bigger in the denominator, that means the denominator is more powerful. So when X gets big, the bottom's going to get big the fastest, making you divide by a very big number, and your horizontal asymptote is at 0. So after I've done my asymptotes, I start my drawing. Okay, so I have vertical asymptote at X equals -7. Another one at X equals 1, and a horizontal asymptote at Y equals 0. With 2 vertical asymptotes, you have 1, 2, 3 sections in your graph. Let's find all of our x-intercepts and our y-intercepts. Okay? Starting with the y-intercept because it's the easiest. Plug in 0 for x, and you get 2 over -7. There's our first point. Do we have any x-intercepts? We do. Again, this is going to feel a little weird. We have an asymptote at y equals 0, but if you plug in 0 for y, can your numerator ever equal 0? Yes. It can equal 0 at -2. So we have an x-intercept at -2. As far as nice points go, do you see you have no points in section 1? We have 2 points in section 2, and we have no points in section 3. So sometimes your x-intercepts and y-intercepts is enough, like in the last example, we could just finish the graph. But this one, we need some more points. So what's a point in section 1? Well, I could just choose any x value less than -7. So I'm going to choose -8. And you could either plug it into the original or into your factored form. I like the factored form because then it's like smaller mental math to do. Can you see the mental math that I plugged in -8 for x? What does that come out to? Positive or negative number? Bottom's positive, top is negative. The whole thing is still going to be -6/9, -6/9, or I could reduce that to -2/3. Then once you have one point, so I've got this point right here, -8, -2/3, that's enough to draw that section closer and closer to your asymptotes. That's all you needed is one point to draw that section. Okay, the middle section. You have 2 points in the middle section. The middle section is kind of interesting. First of all, I hope you can see that if you connected the points there, that to the right, it has to go down. Because if it went back up towards the asymptote, would you not invent another x-intercept? And that would be bad. We only have the one x-intercept. And now, though, there's a little bit of confusion. Because technically, I could make it go up towards this asymptote, or maybe it bounces and goes down. So if you're ever unsure, do another nice point. Like for example, I could plug in, I'm unsure, should it go up towards the asymptote or bounce and go down? I'm not actually unsure, I know what's going to happen, but if I'm a little bit confused, I could do another nice point. What's -6? I'm going to just take out my eraser and erase. Wow, that was bigger than I thought. -6, do you see that you would get -4 on the top? This would be +1, and this would be -7, which is +4/7, -6, positive. Oh, it's going to have to go up towards the asymptote. Well, the other way you could figure it out is what is the multiplicity of our x-intercept? It only happens once, so your graph has to go straight through. If there was an x + 2 squared on the top, it would bounce. Okay? And finally, we need a point in section 3, so I would take out the 2. This time I'm going to take out my smaller eraser and just... Okay? 2 + 2, that's going to be a 4 in there. 2 + 7, that's 9 there. 2 - 1 is 1. You see that you have 4/9? I know we're calling these nice points, but they're all funny looking fractions. We're used to nice points being all whole numbers, right? But it's nice enough because all we need is that point, 2, 4/9, to know that in here it has to look like this. And our graph is done. Here's an example of a graph where the middle of the graph went through the horizontal asymptote. That is a possibility. Right? Horizontal asymptotes just tell you at the extremes, positive and negative infinity, what's happening. So in this example, we had to do 3 additional nice points in order to finish sections 1, 2, and 3. Sometimes your x-intercepts and y-intercepts are enough, and sometimes you have to do extra ones. Okay, so questions to circle. Circle questions 6 and 7.